So in this session I will also summarize different processes we learned so far to form like different dimensional nanomaterials, right? So 3D, 2D, 1D, 0. So we will find the table in this session, and also so during this we have discussed, first we started with what, synthesizing nanoparticles, right? We first started with methods for making 0D nanomaterials. So I'll write it here, methods for making 0D nanomaterials. We started with this. In that, first we discussed PVD. Again, I will not explain because it was explained many times. Even I guess the first lecture, this week you people had 3 lectures, right? And the first lecture, it's just a recap of whatever we have discussed in the last week, right? So after that, the next 2 lectures are solely on what, those mechanical properties, right? So okay, to form discrete nano objects, again, to discrete nano objects is nothing but 0D. You can even call this 0D as 0D. Let me write it in another one. So 0D can only be called as discrete nano objects. So this is what we discussed. Okay, I mean, we didn't discuss, but yeah. So we can call this as discrete nano objects, and to form this we have introduced inert gas condensation. So inert gas condensation, again, you have a gas, you vaporize it, and then you condense it. When you do the condensation, we have a nucleation, and when you have a nucleation forms from very small particles, and those particles are nanoparticles. So nucleation forms from scratch, like from very small, and then it grows. And we do not want to grow, we just stop it by condensing at very minimum temperature so that atoms cannot diffuse. So that's all. That is about inert gas condensation. And same theory was used for inert gas expansion, which is a Joule's expansion or free expansion, you can call it as. So based upon that theory, we create nanoparticles. So again, that is also there. And other crude way of doing is just doing evaporation. And you maintain such conditions, it again get condensed. So that is one thing. And there is also another process which is called as a colloidal methods. So colloidal methods is nothing but you form a colloidal suspension. Okay, so for example, if I have a nanoparticle and then I attach some citric acid or some other polymers, okay, even I can attach a citric acid membrane, and for example, if you form Fe3O4, the citric acid will attach to this Fe3O4 and it will make sure it will not coagulate or it do not form agglomeration. So these chains will make sure these nanoparticles do not agglomerate. So another thing is doing the colloidal solution. And now, what about, okay, so we have discussed 0D, and then we have discussed sonochemical method. Again, in sonochemical method, so the basic theory is just the pressure differences, right? Whenever we used like partial pressure theory, right? So whenever you have a liquid, it will exert a pressure. Whenever you have a liquid, so to maintain equilibrium, the liquid will evaporate, and that evaporated gas will maintain some pressure on the liquid such that whole liquid doesn't get evaporated, right? So that's how. Whenever you have a container, you just fill it with liquid, you just maintain a vacuum for like 5 seconds, then everything will come out. Whenever you do that, after that this liquid will again get evaporated. Why? To maintain pressure, right? Whatever the pressure you have removed here, so whatever the gas molecules that were taken out, and this liquid will get evaporate and it will form gas, and this gas will have a pressure P, and that pressure is given as pure vapor pressure. So yeah, same, the sonochemical method uses that vapor pressure theory to form bubbles, and when you have a compression cycle, these bubbles will coalesce, and whenever you reach a certain pressure, just like a balloon, when you try to pressure it, the balloon bursts. So the same goes for the bubble also. It will burst after reaching a certain size. So whenever it bursts, it creates a very hot spot or very high temperature, and that high temperature will result in again same evaporation of this solvent and again condensing. You will have nanoparticles. That's it. Then we went for sol gel, right? So at first you have a precursor, then you do the precipitation such that the nanoparticles will come out, and you give them time such that these nanoparticles, okay, if, for example, if you have a surfactant, so let's, instead of just saying, let's just explain it in a few seconds. So at first I have a solution, then I add a precipitate forming agent. What does it do? So precipitate, when does a precipitate form? Whenever your solution reaches a supersaturation. So if your solution reaches supersaturation, the precipitates form, right? So your precipitates are formed. Then you add surfactant, and what does the surfactant does? This surfactant makes sure that precipitates do not agglomerate by forming chains, hydrophilic and hydrophobic. That's it. If you want that, so we were at, yeah, so we formed gel. Yeah, we formed nanoporous membrane, right? That's all. So for 3-dimensional structures, we use sol gel. Now if you want to make 1D or 2D nanomaterials, so making 1D or 2D, for that we used this guy to form a 1D thin film of this Micelles, right, which is a self-assembly structures, which is to form 1D films. So again, just dispersing something on a solution, and that will, which has a hydrophobic end, so that it will not get dissolved in it, and everything is on surface. And once you insert something and pull out, this is a separate. So this substrate has the hydrophobic end, so these will get attached. So fatty acid will get attached, and you have a one-dimensional film. So this is a simple way. And then you have this electrodeposition, right? So again, name itself suggests you deposit something by supplying some energy, and that energy is in the form of electricity, right? So yeah, and they have many names: electrowinning or electrodeposition. So electrodeposition is nothing but you have impure anode, and so I will write it instead of just blabbering. So you have a cathode, you have an anode, right? And then you have solution. Same solution goes for here also. So electrodeposition is used when you have impure cathode and pure cathode and impure anode. So whenever you have impure anode, so for example this is 99.9999 pure copper, and this guy is 95% pure copper, right? So what we are trying to do is we are trying to take charge from here. So if you give negative, if it is a positive here. So we are taking charge out. That means the copper will dissolve into the solution and it will travel through the solution and get deposited onto the cathode. That's how you create a pure copper in copper industries. And the other way is you have a copper sulfate solution, you dissolve everything into a sulfate solution or any type of solution, nitrate, chloride solution, and then you apply negative charge here, and what this negative charge will do, whatever the copper was dissolved in here, it will get deposited. So the only difference is in electrodeposition, the ions are coming from anode. In electrowinning, the ions are coming from solution. Okay, so that's the only difference. There's no great physics in there. And yeah, here in electrodeposition, this simple deposition where you take elements from anode and you deposit on cathode. Now once you try to do the deposition, what happens is, so at first some places like this. So once we start the deposition, at first some places it will form, you will have first deposition, and some places it may not. So what happens is, again we are continuously supplying electricity, right? So instead of forming here, this guy grows, right? So you will have this columnar type structure, right? And most of the cases this was the case in I guess some batteries at some, because a factory has designed some different batteries, and for a batch, not the total like whatever they were producing, but for a batch there were faulty batteries, and what was happening was, whenever it was discharged or whenever it was charging, that means something is getting deposited, right? So this deposition wasn't like uniform, it wasn't like a growth, a film growth, like, so it wasn't like this was initially and then the deposition began. This is at time t1. After time t2, this thickness has went down by layer this much, and after time t3, the thickness is uniformly growing. But here it is not the case. So because of this, because of thickness is not uniform, these guys grow so large, they almost like it's not like almost, they just touch the anode. So this was my cathode. So they have grown so large, so they actually touch the anode. So whenever you touch the cathode and anode, that is nothing but a short. So that means you have created a short circuit. And we all know what happens when something goes short circuit. It just creates sparks, and whenever you create sparks in a solution, and that is a flammable solution, and that will explode. So that's why the batteries were exploding. Now here it is not the case. We are trying to grow a uniform thin film. So to do that, what we should do? To grow a uniform thin film, we supply a pulsating voltage. We are not going to like give a continuous flow of current such that those columnar structures can grow. What we are trying to do here is we are trying to supply a pulsating voltages, and pulsating voltages are very simple. So you just, with the time, you stop the giving power supply. That's what we are trying to do. It is at 0 volts, it is at 5 volts. Okay. So for time, this is 1 to 2 seconds, 3 seconds, 4 seconds, 5, 6. So you are skipping voltage for every second. So whenever you do that, so the film that was getting deposited, first here it gets deposited, then because we are shorting the circuit, that means not shorting, we are like breaking the circuit, the next thing that grows will be here. right? So that's how the whole layer will have a uniform, because we are supplying a pulse, because there will be only small crystallites forming everywhere, right? And because we are not supplying the voltage continuously, if you supply voltage continuously, then some of them may grow, some of them may not. But if you do the pulsating, so every time we are giving the same chance for every particle to grow, so that's why you will have a more uniform way of growing. So that's all about electrodeposition. And then, yeah, moving on to PVD. So in last session, I guess we haven't discussed very well on PVD, right? So what is the main advantages and disadvantages? That thing we didn't discuss. So yeah. Now PVD, the name itself suggests physical. Physical means the physical properties like melting point, boiling point, saturation, magnetization. These are related to the physical properties of any material. They're constant. So water's boiling point is 100. It will not change, right? I mean, at 1 atmosphere it is 100. You can boil it at London, or you can boil it in India, or you can boil it in anywhere. It will be 100 degrees centigrade. Yeah, if you're boiling it at, on Mount Everest, that will change, because there the pressure is very low, right? Atmospheric pressure drops. So whenever you have a drop in atmosphere, the boiling point will lower, right? So that's why there is this joke of boiling of water at moon. Even though if you do not have stove or anything, or any heating mechanisms, the water will simply boil at moon. You do not need anything. And why? Because the moon atmosphere is so thin, the boiling point goes very low, right? So it just boils on moon. Yeah, so that's about, you can just refer to this PV, pressure, volume, temperature diagram of water, right? There you can clearly see whenever you decrease the pressure, the temperature also will decrease. The melting or boiling temperature will also decrease, right? Now, so yeah, PVD, physical vapor deposition. So that you have three terms here: physical vapor deposition. So physical vapor deposition. So these are the three things that we have discussed. But yes, physical vapor deposition. Deposition, again, it's nothing but you have a substrate, and then you have some elements. You just make them sit on your substrate, right? So that is a very vague way of saying the deposition, but yeah, most likely it is same thing, right? And do vapor. So the next thing is vapor. So to deposit, you need to first do the condensation, and to do the condensation, you need to first form the vapor. Right? So vapor condenses to solid. Right? So yeah, that's the thing, vapor deposition. And then physical. That means we are using the physical properties like boiling point. So you take any inorganic molecule, you heat it such that it becomes vapor, and then you do the deposition. Simple, right? And that is the physical vapor deposition. And coming to chemical vapor deposition, instead of using the physical properties, we play with the chemical properties. So for example, maybe AB is difficult to deposit, because let's say an example, okay, AB is my molecule, okay, and it is very difficult to deposit because its melting point is, let's say, 1500 degrees centigrade. 15, I said large. So let's say it is 900 degrees centigrade, okay, and you do not have equipment to do the deposition at 900 degrees centigrade. What you will do? You take the vapors of A and B. So A might have the melting point of, so boiling point of 200. B might have like 600. Okay. So So what you do is you form the vapors and then you purge them into a reactor such that they react and they form AB. And this AB gets deposited on substrate or any type of coat or components. You do the if you want to do the coating or anything. That's how. It's very simple and straightforward. Right. So you take the precursors first, then you do the reaction, you get the final product, and then you do the deposition. So that's why people mostly used CVD process when compared to PVD process. So in a variation of conventional CVDs, so if this is the conventional CVD, okay. So there are like moderate temperature CVDs also. So what does the moderate temperature CVD means? And metal organic, you take precursors, so and then you do the decomposition at relatively low temperature. So let's say you take some organic molecule and then you do the decomposition. Ammonium carbonate, for example. Ammonium carbonate is an organic molecule, right? So let's take any not polymer, alcohol, like maybe ethyl tetraethyl alcohol, some sort of chemicals, okay? And then you do the decomposition, and again you purge some other gases, and then you do the chemical reaction, and they get deposited, right? So that is one way of doing. And there is also this plasma CVD. Plasma CVD is nothing but some molecules are so inert, they will not react with the temperature. So you need a plasma to like heat that particular spot to a very high temperature. Then only you can deposit. So for that you use plasma CVD. And if you need little less temperature but still very high temperature, then use laser CVD. Again, laser will also do the same thing. Laser is mostly consists of photons, and photons will hit your surface, they will increase the temperature. And if you have very fine focus laser, then it will make sure such that that localized spot reaches very high temperature. So that is about the laser processing. And then we have plasma enhanced, again for very, if you want the temperatures even reaching higher than the laser one, then you do the plasma. And coatings from these PVD and CVD, again you get 2D coatings, two-dimensional nanomaterials. From PVD and CVD you get two-dimensional nanomaterials. You might even get one-dimensional, and I will explain how that forms in CVD. So let's say you have a substrate. This is my substrate, and then you have a catalyst sitting on the substrate. Okay. Now what I'm trying to do is, now I'm trying to purge organic gases, organic molecules, methane, ethane, or any type, and then I'm heating this region, right? So I'm heating this region, let's say this is my furnace totally, and here I'm purging the gases, right? So these gases will decompose and then they will deposit on our catalyst. And for example, my catalyst, so even straightforward, let's deposit carbon. Okay, so we are depositing carbon on our catalyst, and our catalyst has an inherent property. If something gets deposited or something, it can take carbon, like it can dissolve carbon in it. So just like iron can dissolve carbon, that's how you get steel. So suppose I have some metal which can dissolve carbon. So once the deposition starts, carbon will go into our catalyst. So again, we are continuously purging the gases. So more and more carbon gets deposited and gets immersed or dissolved into our catalyst. And there will be a point where our catalyst will become supersaturated, right? So this is a time t equals to t1, and this is a time t equals to t2. T1 is greater than t2, right? Oh sorry, t1 is less than t2. Yeah. And after some time, because the carbon is continuously getting dissolved into our catalyst will reach a point where it will become just like a sugar solution. You cannot continuously add sugar and hope that everything gets mixed right. There will be a point where the water cannot hold that much sugar, and it will just spit it out. And whatever the sugar was there, it will be at the bottom. The same thing, the catalyst also cannot hold all the carbon in universe, right? After some time, it will start spitting out the carbon, and once it reaches the supersaturation, it will start spitting out. And how does it spits? This catalyst will spit the nanotubes, and these will grow. That's how it happens. So this catalyst, after reaching supersaturation, it will start giving out the carbon, right, which was dissolved in it, and that carbon will come out as CNTs. And most of the CNTs are multi-bond CNTs, not single bond. It is very difficult to make single bond CNTs, and also whatever the CNTs you create, again it is CVD process, because you took a chemical or a molecules or organic molecules, and then you did the vapor, and then you are doing the deposition. So from CVD you will not only can do the thin film deposition, you can even also do CNTs, and CNTs are one-dimensional nanomaterials, right? How everyone knows CNTs are one-dimensional because the radius is in angstroms, sorry, not angstroms, in nanometers, right? 1 to 100 nanometers. So our circle has x and y axis, which are in nano range. That means one dimension is not in nano range, so that's what we call it as one dimensional nanometer. So CNTs are also created, and most of the CNTs created from this are multi-bond nanotubes, not single bond. Single bond is very hard to make because then you need to have very fine catalyst, right? Because whenever you have a big catalyst, here also the CNT grows. It can grow like this. So that's why you see a multi-bond. Multi-bond is nothing but, if this is my single bond, then you have a port structure. So there are so many bonds. This is how CNT looks like, right? That's why guys. These are multi-bond carbon atoms, and if you have only single bond, so this is a single bond carbon nanotube. right? I hope you will can differentiate. And to form single wall nanotube, we need to have very fine particle of catalyst, nanoparticle of catalyst. Then only the maximum wall radius we can achieve is single wall. If you have a big catalyst, then there will be so many walls that are formed. If you have a very fine catalyst, then the radius should be such that you can only form one wall. So that is about single wall nanotubes. And in this process, you will have so many, not so many, so much of what do you call it? The waste material, or you can call it as a defects. And where this defect come from? Because of the catalyst pickup. And see, after some time, the CNTs grow so large, they start bending, and when they start bending, they even rips out. They might even rip out the catalyst itself, right? So whenever the CNT becomes so large, it can rip out the catalyst from the surface. That is also a case. So when that happens, the CNT growing will stop. Right? So that's the one way of making CNTs. We have completed PVD, CVD, and I have explained the major differences. So in CVD, all you need, you can do your experiments even at lower temperatures. When compared to PVD, PVD is basically taking the physical properties into account, but in chemical deposition, vapor deposition, you take chemical properties of molecules. Now, and the next part is rapid solidification. This is called as so what do I mean by rapid solidification? So there is the way of saying, when you cool things slower, I mean not slower, if you cool things very fast, you can make glass of anything. People have tried it. One guy formed gold glass. So how did he form gold glass? So gold is crystalline, right? Gold is crystalline. Right, so gold is a crystalline and glass is amorphous. Unless there is no periodicity in amorphous, but there is a periodicity in crystalline. And people have tried forming gold glass. How did they form? One guy, what he tried was, this is, let's say this is a stopper, and he melted gold, okay, and then he applied a very high pressure of gas from above. Right? It's just like taking water in your mouth and spitting it out at very high, fastly, right? So what do? You apply air pressure from your lungs into your mouth, such that the water will come out from your mouth as a jet. Right? So that's what's same here happening is, he applied argon gas, which is an inert gas, from here, and the gold, when he applied very high pressure, this stopper will break. So it was designed in such a way, whenever you apply high pressure, it will break. Okay. So for example, he applied 50 megapascals. Okay. Or you can say he did apply a 10 bar pressure. So when it reached the 10 bar pressure, the stopper broke and gold started to pour out from this right, at a very high speed. And whenever it comes out from a small orifice, and because there is a air also, so it will form a small droplets. So he found very small droplets of coal. So now, and then below he had liquid nitrogen. So liquid nitrogen has minus 196 degrees centigrade. I guess, yeah, minus 196. I guess it is, I hope I am right. It is, I mean, in that range, minus 195 or 190 range, okay. So it is at minus 186 degrees centigrade. And these were directly immersed into liquid nitrogen, right? So there is a very rapid cooling, and also the droplets were very small, right? So whenever you have a very small particle, the thermal gradient will be very fast. If you have a large particle, then the thermal gradient will be there. So that's what the Biot number gave, right, in fluid mechanics or heat transfer. So Biot's, I hope I am right. Biot's number, I don't know exactly what the term is. So Biot number tells you what should be the dimension, the conductivity, and so yeah, one is the dimension, other is the conductivity. Yeah, so these two terms is defined by convection. Okay, so you have conductivity, and then you have dimension, and then you have convectivity. Convection, right? So heat has three way of forming: conduction, convection, radiation. Conduction is mainly on phonons, where the collective oscillation of atoms. Right? Please don't confuse with plasmons. Plasmon is collective oscillation of electrons. Phonons is collective oscillation of atoms. That's how the heat transfer takes place via conduction. Right? So yeah, and that is one thing. And then you have convection. Convection is basically through the convective flow of gases. Flow of medium. And then you have radiation, right? So see, there is this minor change or minor difference between conduction and convection. So whenever we're trying of conduction, we say that the movement of heat inside a solid, right? So movement of heat. So for example, this is the temperature T2, this is the temperature T1. T2 is greater than T1. So the heat will flow from here to here, and the temperature will decrease from this to this. Right. So conduction is more or less the oscillation and movement of atoms. It's not like the atoms. So this is the steel material. If I am heating a T2 and T1, the atoms will start oscillating, and they transfer energy from here to here. So let me explain it more clearly. So this is at high temperature, right? So the atoms, so it is at higher energy. T2 is at higher temperature. T2 greater than T1. So that means T2 is at higher energy. Higher energy means higher oscillations. So here the atoms are oscillating very fast. What about T1? T1 it is at lower temperature. So the atoms are oscillating slow here. Now, this is how the energy is being transferred from here to here. The oscillations. The higher energy oscillations have higher energy, and this energy is being carried away from here to here. Right? So it's not like atoms itself are moving. Right? In solids, atoms cannot move. Right? They cannot move for longer distances because everything is so dense they cannot move properly. So So that's how the heat will go via the oscillations, and that's how it happens in conduction. Next, it is convection. In convection, you have free motion of atoms, like in liquids, in gases, in fluids. You have very free motion, right? So conduction is done, convection is done, and then you have radiation. So radiation happens without a medium, right? So it happens in more or less wave packets, right? So it's photon wave packets, you can call it as, right? You can just call it as a wave packet because people have this confusion with photon and light, right? So it's not confusing. Just you can say radiation happens in terms of wave packets, energy packets. That's what we learned from Maxwell, right? So yeah. So whenever you have this cooling, very rapid cooling, and whenever you have very small particle, the thermal gradient will be very small, such that the cooling is instantaneous throughout the body. And whenever you have very rapid cooling, so whenever you have a liquid means the very random arrangement of atoms. The atoms are continuously moving, there is no symmetry at all, right? I have a liquid first. Liquid means no symmetry, random motion of atoms, they have higher energy, and when you cool it down, you form solid. May have symmetry, no random motion, low energy, and densely packed. This is our solid. So whenever you just cool it very fast, okay, and you form a solid, then instead, so whenever you cool it, the atoms will start rearranging themselves. So before cooling, you have liquid, which is the random arrangement, so random motion of atoms, and when you start cooling, the atoms will rearrange themselves into a symmetrical way and form a solid. So that's what we see everywhere, even in ice. Whenever water gets cooled out, it will form crystals, ice crystals. It has symmetry. Same goes for iron. Same goes for any metals. Okay, so they tend to have a good symmetry. It means densely packed, low energy, everything will go. So that's about solids. So whenever you suppress this time, right? So what I'm trying to do is, I'm not giving time. So delta T is very small. Cooling is fast. What I'm trying to do is fast cooling. So I'm not giving time. Not further arrangements. So you are not giving time at all for the atomic arrangements. Right? There is no rearrangement at all. Then what happens? That means you are retaining them in, and because my liquid is in amorphous state, so whenever I cool it very fast, I am doing is thermal arrest. We call it as thermal arrest. That means we are arresting the motion of atoms. We are not making them so that they can rearrange. We are not giving time. We are not even giving energy for them to rearrange. We are just taking that energy out very fast. So then we will have a glass. That's how the glasses are formed. Whenever you cool any metal very fast, you will have glass. So the same thing here. And the drum is very cold and it also is spinning at a different RPM. It will just splash the liquid, and this splashing will give you an amorphous crystals. And if you want a strip, right, you can even just form a strip. You do not spin it very fast, you spin it very slowly, and the material will start, when you start pouring, the material hits here, it will become solidified, and when you start spinning, you will have a strip. That's how you form a strip. And then you have the laser surface melting. And what do you mean by laser surface melting? So again, the same, laser is made of photons, so very fine modulated photons, right? So these photons hit a surface, and when you, photons are nothing but energy, so you are supplying energy continuously to a system at a very small point, and it will start melting, and when it starts melt, you start moving, right? And whenever you try to move, whatever the melted region will now become solidified. And if some metals may form glasses even if you cool it normally, right? If you are not doing very fast, right, you are not introducing any liquid nitrogen or anything, you are just cooling it, right? So that's what I mean. We are not cooling or any sort. We are just making sure that we are just moving all this. That's what we are doing. And then I have gold beating or foil beating. So beating, and it is done for very tactile materials. What do you mean by very ductile? Ductility is nothing but, again we will discuss this in few minutes. So ductility is nothing but the ability of a material to deform without undergoing fracture. Fracture is nothing but breaking. We have seen bone fracture or many things, right? So breaking, deforming without breaking, that's what we called as ductility. Okay. Now, yeah, as a guys, we have discussed this, so there is no need to discuss again. So the same laser ablation, laser surface melting, melt spinning, and here you just deform in a such a way that you have elongated grains. So whenever you have, let's say 1 mm cross 1 mm, and you start deforming it, right? You start stretching it, and this at some point it may become 50 micrometers, and this length will be increased many times, right? So maybe 1 meter, and then again if you start stretching, this thickness may become in nanometers, right? So that's what we are doing. We are making sure that grains have 1 nanometer in them. And then you do the powder milling. Powder milling is nothing but you just break the particles. So milling can be done in many ways. Milling can be done solely for mixing. So for example, if you have A powder and then B powder, and if you want to mix, you do the milling, right? So let me write it somewhere else. So for mixing, you can use milling. For mixing two powders, A and B, you can do the milling, or if you want to reduce the powder particle size, reduce the powder particle size. Again, same, you can do the milling, or if you want to make a reaction, you want to I have some connectivity issues, but still I hope I am back. So yeah, it is okay. It is running again. Yeah. If you want to do the reaction between two species, A and B, again you do use a milling. So all the difference here is the energy that you are supplying. So for just mixing, you give a very less energy. So where this energy is coming from? The energy is coming from the collision of balls, or the collision between the balls and the powder particles. That's how this energy is coming from, right? So this energy is coming from the collision between the powder particles and balls. Now, and if you do at low RPM, the energy is not very large, it's small, so there is no even breaking of powder particle. So that's why we do the mixing at max to max 860 to 90 RPM rotation per minute. If you have planetary ball mill, sorry, not planetary, high energy ball mill. So if you have energy ball mill, so ball mill actually looks like this. You have a rotating stage. So this is my rotating stage. Okay, and then this is the high energy ball mill that we have in our lab, and then you have 4 slots. Okay, and these 4 slots are rotatable. I mean, there is no attached motors to it. Okay, so they are just not hinged. Okay, so whenever this rotating stage rotates, they will also rotate. Okay, so because they are not hinged and they are fixed at their position, so we put balls and powder here in these slots, and we pack them with a lid. So to balance weight, we put same amount of balls into this guy. So yeah, and then we rotate it. So because of this rotation, the balls inside the jars also will get rotated and they will collide with each other. So there is energy transfer, and whenever a powder particle comes between them, just like here, whenever a powder particle comes between the two particles, the powder particle will break if the balls have high, what do you call it? High enough energy, right? If you are rotating at very high RPM, so for example 120 or 140 RPM, then the balls have some enough energy to break the powder particles. Again, To break the water particles, it depends upon the inherent property, whether it is ductile or brittle. If it is brittle, then you will have, it will take less time to form the water particles, and if it is ductile, then it will take large and large amount of time, because whenever the water particle comes in between the two balls, so for ductile, say this is okay. If I have a brittle particle, it will break. Right, there is this breaking. And if you have a ductile particle, it will just simply deform. It will not break, it will deform, just like here. See? It is just getting deformed, it is not getting break. So it will take lots of time to do the milling. And then you have a micro machining. People have seen this micro machining everywhere, even in lathe machines. So whenever you have a cutting tool and you have your workpiece and you do the machining, so the cutting tool will take out the chips, so that those chips can be also used as nanomaterials. And then there is this other thing called pressure sintering. Okay, so I guess sir has discussed spark plasma sintering, right? Spark plasma sintering. So it's nothing but you have your water particles which are packed. So you have water particles. So these water particles are touching each other when you make it a compact pellet. Green pellet. Green pellet is nothing but you apply pressure. So you create a die. Simple. You have a die. It has a hole in it, and you put a stopper here, and then you pour powder, and then you apply pressure from this die, which can be done by applying either hand or just pressure valve. Okay, so you will have a pellet. In this pellet, the water particles are touching each other, which is obvious, and then you apply current. So whenever the current flows inside the water particle, it is okay, but when it is crossing the path, there you have a resistance, but you can call it as a contact resistance. And whenever you have a contact resistance, there you have a contact resistance, and whenever you have a resistance, I hope everyone remember this, Joule's heating. So whenever you have resistance, you have heat. Right, and also we are supplying very large amounts of current in spark plasma sintering. Right, so that's how you have a localized melting spot. And not only that, here whenever you apply very large amount of current, so there are many ways of heating here in SPS, spark plasma sintering. So we only discussed about so first thing, supply of huge currents, kiloamps. Okay, and then so this is I 0.1 and this is 0.2 contact resistance. That means Joule's heating. So this will get melted and this part will get fused. And the third thing is, because we are supplying very large current, there is a buildup of charge here, right? Because there is, whenever you apply current, then there is also voltage, and because you are applying very high amount of currents, you will have very high voltage here. So high voltage. So the voltage is very high on the surfaces. Why? Because the current cannot flow here, and also because you are supplying very high current, there is also voltage here, right? Current is flowing through here like this. Throughout the material, the current is flowing, right? So that's how. So that means you have a certain voltage on your particle, and same goes for here also. This current will flow here. Again, you have voltage. So let me draw in different color. Okay. Take yellow. Okay, so okay, this is the melting, right? The fused zone. Same. So there is very high voltage on the surfaces. And whenever you have a high voltage, so for example, if there is a trapped gas in here, so what we try to do, we try to purge argon or we try to maintain vacuum. If you try to maintain vacuum, then it is good. So for if you take vacuum, then it is a direct way. The current just passes through the air because of breakdown, right? So let's not take easy way. Let's take the difficult way. So let's say I have air here. Okay. So whenever I have very high voltages, right? So I have very high voltage. And because of this high voltage, here I have gas molecules. That means air is nothing but gas molecules. And because of this high voltage, for example, if I have, let's say, this is my atom, positive, negative, right? And when I apply voltage, if I apply positive voltage here, then this positive charge will shift towards this side, and negative charge will shift towards this side. So that's we call as polarization, and that is an induced polarization because we are inducing charge because there was a neutrality. Still there is neutrality, but we are making sure that the positive move our way and negative will move that way. So there will be polarization here. Okay, let me write it in green now. So then you have polarization. So same thing goes here also. Minus, plus, 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 minus, plus. So you start polarizing your air, right? So you start making polarizing your air, and once you start making polarizing your air, then there is a charge forming in air molecules, right? So there is a charge distribution in air molecules. Once this polarization, so again, I will draw. So this is very interesting theory, this polarization. That's how the thundering, everything happens. thunderstorms, wherever you see the thunder, the same thing happens, right? So let's take yellow. Yellow was for this, right? So you have your voltage on this line, and after that you have the polarization, induced polarization. And this polarization will not stop, and because there is a very high voltages, this guy, this whatever the polarized, will again polarize the near molecules, right? Because see, this guy have plus, and this polarization will result in minus plus, and this plus will again attract minus of other molecule, right? So my polarization will start, this layer will start decreasing. I mean, more and more polarization will happen, more and more. So at a point, everything is getting covered in charges. So once you have charge, what happens? My current will flow through here also. How? In the form of spark, just like a thunder, right? So I have conventional current flowing here, conventionally, not conventional current, okay? Conventional flow, not conventionally, okay? So conventional flow of current. Here it's not conventional flow, it is breakdown voltage. You are breaking down the gas molecules, because gas is perfectly or plus minus, it's like charge, I mean charge neutral, but you are breaking down such that the positive and negative goes sideways, right? Just like this, the induced polarization. So you break down these air molecules, and this current will flow like this. Like this also the current will flow. How? The spark, it's like I draw according to my imagination. So that's how again the spark will flow. So then I have spark, and the next thing is plasma. So whenever you have very high current flowing through your gas molecules, very high current is flowing, right? Because you are supplying very high current, and this high current will make sure the electrons comes out. This has very high energy such that you will have positive ions. The electron will come out, and then you have positive ions. So there is a creation of this plasma. So that's why we call it as spark. And this plasma again has very high temperature. This plasma will emit the radiation. This radiation will heat this surface also. Not only this guy is getting heated, now this guy also will get heated, right? And everything becomes liquid, because these guys are heating, right? They will become, this surface will become very soft and starts melting, and then you have sintering. The spark and plasma combined will give you sintering effect. So that's what we call it as spark plasma sintering. So this is what happens there. I hope you people are clear now. Nanoprofiling, same. You take laser, you melt very fast. You will have a small nucleation happens, and nucleation means small nuclei, very small in nano range. You will have a nano, what do you call, profiling. That's all. Here you are using electron beam. Electrons mean electrons are accelerating. So that means energy. So high energy means if you are making electron to collide a surface, they will heat it up, melting, and then you cool, nucleation, small nuclei, profiling. That's all. Here it is a laser. Here it is a plasma. Same. There's no very big difference there. And this is very much important in in semiconductor industries, it is lithography. So lithography's methods are mostly use of mechanical process, like printing, stamping, molding, etc. So here we do not use any mechanical part. We use light. So how do we do that? So here what do we do is, our starting material is silicon mold. Okay, so we start with the silicon mold. Let's say this is my silicon mold. Okay, now and then you have a silica above it, because the silicon, if you put it in an oxygen or environment, you will have a layer forming on it. This silicon will react with oxygen and it will form a layer of silica. Okay, then what you do is, then you apply a photoresist material. So it can be a positive one or it can be a negative one. Okay, positive is nothing but it will, whenever you apply UV beam, it will react. That is positive. If it is negative, that means it will not react. That's it. There is nothing different. Okay? So here let's say the positive, that means it is reacting. So you apply photoresist and then you put a mask and then you pass through the UV, or you apply UV light. So UV light will go through it, and wherever the mask is not there, it will react with photoresist. And then if you react with any acids, this photoresist, whatever the reacted, will get away. Okay, and then again the silica layer can be also etched with some acids. So see, this layer will be eaten away by acids. Now I am remaining with these guys. So what I will do, I will remove the remaining resist and then I will etch the underlying silicon. So what I am going to do, I will etch this part. Okay, because SiO2 is stable. SiO2 will not react with most of the acids, not most, some of the acids, and we use those acids to react with silicon only. Selective dissolution. This is called as selective dissolution. Okay, so yeah, that is about selective dissolution. That means you selectively dissolve one part and you make sure the other part will not get dissolved. So that's how you will get the selective dissolution term. And this is our summary. Okay, you can get this summary in this book, Michael F. Ashby, which everything I have been using to demonstrate here. Okay. Now same for particles, I have inert gas condensation, free jet expansion, sonochemical, sol gel, molecular self-assembly. And there is a small mistake here. If you want a discrete, so sol gel, I have to write discrete particles. You can use sol gel there. And then wires and tubes, CVD, again I have discussed how you have a catalyst. And then CNT grows. So molecular self-assembly I have explained. And then films, you can have micro machining or patterning, same. Focused ion beam, same. Electron beam, thin film deposition techniques, electrodeposition, my layer continuously moving. So sputtering, again, sputtering is nothing but you, suppose you have a solid, you supply voltage to this solid. Okay, so this is my solid and I am supplying voltage. So for example 50 kV. 50 kV is very large, so very large, 50 kV is very large. Okay, then what happens, because of we are supplying very large amount of energy, the atoms will come out from the surface. Okay, these atoms will again get deposited with him. Let me explain it more clearly in the next slide. So this is my atom, and this is getting, okay, this is my solid piece, and supply of voltage 25 kV. That is very high, but still it is very high voltage. Okay, because 25 kV is used in railway lines, right? Now, and because of supplying a very high amount of energy, the atoms will come out. Okay, and what I am trying to do is I will purge argon gas here like this, and this argon gas will carry these atoms, whatever the atoms that are being taken out, and you have a cold surface, and they get deposited. That's it. That is called sputtering. It is same as PVD CVD, but the only thing is, instead of melting or doing any reaction, we just supply very high amount of energy to the surface piece, and the atoms will come out and they get deposited. That's what we call it as a sputtering. That's all. So there is other thing, foil beating. I have explained this. CVD also have explained this, and I didn't explain molecular epoxy, but I will explain in next few lectures. Okay. So yeah, photography, and in bulk form also you will get one sintering, okay, compaction, okay, equiangle extrusion, and also sol gel. You people have forgot. Sol gel, we can make discrete particles also. We can make discrete particles and porous 3D structure. Please do not forget this. We can even make porous 3D structure. Okay, then now the most important part of this nanomaterials and the properties, right? So we are coming to the next part of this whole course and their properties. So the first part is the mechanical properties we are going to discuss, and then maybe electrical, and then magnetic, I guess, because we are not going to discuss acoustic. Acoustic is mostly related to macro particles, right? So acoustic will not be very much introduced here. So we will discuss mechanical, electrical, and magnetic. Is there optical also? How can you forget this optical? Because this is where we learned SPR, right? So yeah, and yeah, that's it. Electrical, mechanical, electrical, magnetic, optical. If time allows, we can do the characterization also. I will try to explain, if the time allows, I may explain it in the last lecture, or we will have an extra session. You will get an email regarding to this when it is going to be. So in this session I will explain how do you characterize this nanomaterials. We have different machines in SEM, FESEM, field emission, FESEM, field emission scanning electron microscope. It's a one type of electron microscope where our electron gun is field emission material. So yeah, you apply field, it emits electrons. That's it. And there is also a tungsten gun. In tungsten gun, what you do is you apply voltage. It's more like a thermoionic emission. You heat it, it emits energy, right? But field ion emission is not like heating. It's just to supply electric field at the surface, and they will strip out the electrons. That's what happens in field emission. So that is the difference between thermoionic emission and field emission, right? And in FACM you can see the nanoparticles. In TEM also you can see nanoparticles, transmission electron microscope, and these are very like expensive things. And there is one thing of measuring these nanoparticles, that is UVs. So ultraviolet visible one. So if you use that, you may not see or measure the nanoparticles, but you can say that this sample contains nanoparticles. So how it happens is, it's because of SPR. So see, that is the importance of this SPR. This SPR will tell you when you do the UVS whether you have the nanoparticles or not. There is this hump forming. I will explain this when we do the optical properties, okay? So yeah, coming to the mechanical properties. So mechanical properties, mostly if we are only touching the scratch, if we do the scratch part, then we will stick with only two characterization techniques. One is two techniques. One is tensile testing, and next one is the hardness test. So these two are the most widely used testing techniques to measure the properties of material. From hardness testing, you will get the hardness values of the material. That is one point. And from tensile testing, you can get many things. You can get yield strength, you can get elastic modulus, you can get the flow curve, the deformation flow curve, constant terms, and you can get many things from tensile testing. Okay. So what is the ductility? What is the fracture toughness? And there are many things. Okay. So moving on to, so again there are three types of static stresses to which the material can be subjected to. It's simple. How many types of forces that we can apply? Suppose you have a box, you can press it with your both hands. That is called as compression. That is the one thing you can do. And the next thing you can do is stretch it. That is tensile stress. It's a compression stress. That is another compression, applying of compression stresses. And the second thing is the application of tensile stresses. And the third one is you shear it. I mean, you keep one hand and move it in this direction, and you keep another hand and move it in this direction. This is called as shearing, and we call it as shear stresses. That's it. These are the three forces that you can apply. That's all. And people might say, okay, what about if, my bad. So people will say, what happens if you apply a stress like this? It's simple, you just resolve it. So one component will be my shear stress, one more component will be my tensile stress. So everything can be resolved in this, right? So these are the three types of stresses that we can apply on any material. And the stress strain curve, which is like the most basic thing you learn when you join metallurgy. Right? In physical metallurgy is like a basic course or introduction to metallurgy 101. It shouldn't be called as physical metallurgy, but it's like an introduction to metallurgy 101. Okay. So in there you will learn what are the different things in metallurgy. Right. So there you will come across this stress strain curve. Yeah, and to do this stress strain curve, what type of forces you apply? You apply tensile forces. And so how the sample should look like? The sample should be either a rectangle or a cylindrical, and there should be a like what do you call it, a branch type for which you can hold your sample. So that's why most of the tensile sample will look like this, a dog bone shape. It looks like a dog bone structure. See, you can see here. And yeah, so this is my stress strain curve, and the stress strain curve are of two types. One is the engineering stress strain curve and true stress strain curve. True stress strain curve. See, so the basic difference is depends upon what are the initial parameters. In engineering, stress is nothing but force upon area. This is the initial area. Okay. In true stress strain, this is for engineering. For true stress strain, the stress will be equals to load upon the instantaneous area. So it's like instantaneously you are measuring the area and then you do the. So we mostly use the engineering stress strain curve because that is easy to visualize and understand when compared to true stress strain curve. Okay. So true stress strain curve is mostly used in industrial purposes. Okay. So at basic level understanding, you can use anything, but people prefer engineering stress strain. Okay. So at first the material will behave as a plastic one. Okay. So when you increase stress, so let me draw something. Yeah, this is the difference between engineering stress strain and true stress strain curve. Okay. So then because my area is constant, so area doesn't depend, it only depends upon load, so that's why more load will get decreased. But here my area is also decreasing, that's why this value gets increased. That's all. Coming to here. So yeah, I have prepared my tensile sample and I put it in a tensile testing machine and it starts stretching it. So at first my particle will behave as a elastic rubber. So if you stretch an elastic rubber, it will regain its original position. The same goes here. If I apply stress, it will elongate, and if I remove stress, it will come back to its initial position. The same goes for if I apply more stress, it will elongate even more, and if I remove stress, it will again come back to the same position. So more like a rubber band. And once I reach a point, which is called as the yield point, and there are many points where, see, it's very difficult to define when to define. Okay, so you have an elastic region, you have plastic region. So the next part you see is a plastic region. Above this part is plastic, below is elastic. I shouldn't say after this point it is plastic, below this point it is plastic. Okay, elastic, sorry. So now how do you differentiate when to start plastic, right? There are many debate and these things. So people have like created many points. One is the yield point, where the material starts yielding, that means material starts deforming plastically, and there is this point called 0.1% strain. Okay, that means 0.1% of strain is not being for example, once you start this point, this amount of strain is not being recovered. There are different names. Okay, so it's best to, for now, let's just take yield point as our differentiating region of elastic and plastic. So from elastic you can get elastic modulus, and what does elastic modulus say? So it tells you how our stress, what is my stress strain relation in elastic region. And because it is a linear curve, you just write it like this. Instead of G, let's write it as Y. Okay. Y is equal to K, mx. Simple relation. And in plastic region, you have this complex curve. Right, because it is a curve, so you need to have an equation like this. Right, we do not know what is the exponents and curves. And so let's solve. And here we have a perfectly elastic. There is no deformation. It's just like a rubber band. And here it is perfectly plastic. What do you mean perfectly plastic? That means once you reach this point, you don't need to apply stress. You need not increase stress. The material will continuously deform, just like water. If you try to disturb the surface, it will deform itself, or it will move itself and rearrange. Same goes for it. All you have to do is you reach this point and you maintain that stress, it will continuously deform itself. That's all. That will be called as perfectly plastic. And this is not, this is for metals, which we see. Okay? Now, the other testing is hardness testing. So hardness testing, you have Brinell and Lockwell. So why do we have different types of testing? Because the material hardness is not same, right? So for example, iron has some higher hardness when compared to aluminum. You cannot use single process, right? Because the material which we are trying to use to deform the material maybe not tougher than the material you are trying to deform, right? So then you need to change your hardness testing. So it's basically the which hardness material you are using, what is the grade of hardness, and you are trying to deform. Okay, so that's all. Now finally coming to this. Coming to this deformation part, right? So Sir has delivered very complex equations for this Hall-Bridge correlation. So what I'm trying to do is I will have very simple relation, okay, instead of so many things. So simple. So whenever you have a grain boundary, so the deformation happens via dislocation motion. So deformation takes place in two ways. One, dislocation motion. Two, twinning. Dislocation motion is nothing but movement of some movement of one atomic plane at a time. But twinning is a collection of movement of atomic planes. So it is a vague explanation, but still it is to understand normally. So you can even look it into it. You can see what is the main difference between the dislocation motion and twinning. Right? In dislocation motion, you will have every time you have only one or two atomic planes moving. In twinning, you have a collection of atomic planes moving at a time. So these are seen in like HCP, BCC materials, and this is dislocation motion is seen in mostly ductile materials, FCC, BCC. Okay. So and whenever you're trying to deformation is nothing but dislocation motion, and it's not like grain has only one dislocation. So for example, there is a source or not even source. For example, the dislocations are moving, and you know this is grain 1 and grain 2. The difference between grain 1 and grain 2 is the atomic planes arrangement, right? If this is my atomic planes direction, here my atomic planes direction might be like this. See, there is a change in direction. Then, so slip system, so every material has, every FCC or every material has a certain slip system. In FCC materials, mostly it is 110 direction, okay, and 111 planes, right? So you have 111 plane, and because dislocation motion happens mostly in closed back plane, and FCC closed back plane is 111. So, and the dislocation motion is in 110 direction. Right, so that is about that. And in grain 1, 1110 direction is like this. Here 1110 direction is different. Then how this dislocation will move, right? So here comes the problem. So this is my grain boundary. Now I am applying applied stress. So I am applying stress. That's why my dislocations are moving. And once they reach a grain boundary, they will start getting piled up. Okay, so, and because of this pile up, there is also the back stress. Right now, and this stress will be resolved. Right, so whenever you have a surface applying on a stress, so this surface will get, it will be resolved. So you will have resolved critical stress, or resolved shear stress. This is a shear stress, right? Resolved shear stress. And let's say the number of dislocation is n, and tau c will be the critical stress required to initiate dislocations or move the dislocations from one grain to another grain, or initiate the dislocation motion on this grain. Right, so this is called as a critical shear stress. Critical shear stress to initiate dislocation source in grain 2. This is grain 1. Right? Now, whenever you try to move a dislocation, there is also a lattice friction, because the lattice planes are also, you need stress to move lattice planes, right? So what is the minimum stress to move this? So that is given as, let's write it as frictional stress. The stress, frictional stress coming from lattice. Okay. So what is my critical shear stress? That is will be equals to n times the resolved shear stress. Right. If you have n number of dislocations, if you have one dislocation, then that critical stress will be equals to the resolved shear stress that is applying. That is here. Right. If there are n, then n times that one. Now, what is my shear stress or resolved shear stress, which is equals to the applied shear stress minus the lattice one, the frictional stress. Now, what is my shear strain? Shear strain will be equals to the amount of movement in atomic planes, that is given by, so each dislocation can move one Berger vector at a time, right? So B, and if there are n dislocations, then NB upon total length. This is the total length they are moving, right? L. What about shear stress? Shear stress can be given as shear modulus into strain, shear strain. Now what is my N? N will be equals to N will be equals to shear stress or the resolved shear stress times L upon GB. Now we know critical shear stress that requires to initiate dislocation source on adjacent grain will be equals to tau C will be equals to N times tau S, because you already have tau S, right? So that's why you have LGB tau S square. Now what is my tau S? Tau S will be equals to LGB tau A minus tau I whole square. This is the applied stress. Because we know the applied stress, we do not know the critical stress that is required, right? We might not exactly know the frictional stress that is there. So that's why you take everything that side. So I plus GB upon L into DC whole power 1/2. So TA will be equals to Pi plus K L power minus 1/2. This is all of its correlation. This is the applied shear stress. There is a the frictional shear stress inside the material plus the constant term K, all which is constant, into the size of the grain. So the applied shear stress or the yield strength is inversely proportional to the grain size. So this is for like what? The bulk materials, but these for bulk materials. And if you go to nanoparticles, and because the nanoparticles have high surface area and they are very small, they cannot accommodate dislocations, first of all. That is one thing. The next thing is, and because the surface energy is so large, there will be a sliding also here. So because of all these reasons, the yield strength will drop instead of increasing. See, this is my size of grain in mm. If you take, it will increase to a certain value and then it will start decreasing. Why? Because of these reasons. Because because the dislocations are very hard to accommodate inside a nanoparticles, and these nanograins will also like slide on each other, right? So these are the few reasons, and because of this, here you have Hall-Petch correlation, and this region is called as inverse Hall-Petch correlation. That's it. Okay. So I hope you people able to understand this part, because this is the most easiest derivation, because you cannot get simpler than this. Okay. So that's it for today's session. We will meet in the next session. So if you people have any doubts,